All right, so let's get started here. We're going to continue talking about solution reactions. This particular lecture is going to feature heavily a new addition to our constants page, what's called a solubility table. And just like all of our constants page, our periodic table, our solubility table, they can all be found under the introduction for that week, right? So if you click the week 6 introduction, you have all 3 of those resources. And again, we're going to introduce this new one here today, this solubility table. All right, so that's how you go about finding this particular tool we're going to use here. Okay, so we're going to use this table right here to talk about the solubility of ionic compounds. Okay, so first of all, what the heck do I mean by solubility? A soluble compound is a compound that will dissolve in water. And if we can take that compound and dissolve it in water, that means that we can create an aqueous solution with that particular compound, right? So if it's soluble, we can say we can create an aqueous solution. Many ionic compounds are soluble in water. Sodium chloride, we know well, if we take salt and we put it into water, we can mix it around and we can get it to dissolve. All right? But there are a lot of other compounds out there that will not dissolve in water. And these are what we call insoluble compounds. Insoluble compounds are compounds that will not dissolve in water. So you couldn't create an aqueous solution with these insoluble compounds. All right, so again, we're going to start with one that we know intuitively, table salt, sodium chloride. All right, I think we've all seen that sodium chloride does indeed dissolve in water. So given a formula, NaCl, we need to be able to use this table here and identify whether that compound is soluble or insoluble. All right, that's the name of the game here. All right, so what we're going to do is we're going to look up our ions on the left-hand side. And it's usually easier to find the anions of that particular, of your ionic compound. All possible anions are listed here. There are only a few special cations that are listed here, okay? So what I'm going to do is I'm going to use my table here. In this case, I can actually find both of these ions on my table. All right? Notice how this table is broken up into these columns. The first one is titled water-soluble compounds. Right? And then the next column is the insoluble exceptions. Okay? If we look up sodium on this table here, we see sodium in this very first box here. It says that if your compound contains sodium, there are no insoluble exceptions, meaning every sodium-containing compound is a soluble ionic compound. Okay? Again, normally it's easier to find the anion, the negatively charged ion, so let's just convince ourselves that if we do that, we get the same answer here. If I look up my anion, my chloride ion, everybody take a second, see if you can find the anion on the left-hand side here. All right, what box is that in? This third one right here. Okay, this tells me that most chloride compounds are indeed soluble, but there are a few insoluble exceptions, right? And that's when chloride is paired with silver, mercury, or lead. In sodium chloride, do I have silver, mercury, or lead? No, so that means that this compound is indeed a soluble compound. All right, let's do another one. Okay, we're going to do PbBr2, lead 2 bromide. All right, take a second to find that anion on the left-hand side of our table. All right, notice it's also listed with chlorine, right? So all of our halogens are listed together, the chloride, the bromide, the iodide. All right, and this is telling me that most bromide-containing compounds are indeed water-soluble, but there are a few insoluble exceptions. And one of those insoluble exceptions is when a bromide ion is paired with lead 2. Right? So in this case, this compound would be one of those insoluble exceptions. So this is insoluble. Okay? I'm going to put down 2 more here, and you're going to do these on your own. All right, calcium sulfate and magnesium sulfate. You're going to use our table here to tell me whether these compounds are soluble or insoluble. All right, I'm going to give you a few minutes and then we'll go over them together. Zoom in as much as possible here. You're going to look up that anion, that sulfate ion on the left-hand side of this table. All right, so let's take a poll here for this first one, calcium sulfate. Raise your hand if you think it's soluble. And what about insoluble? Awesome. Okay, so this one is indeed insoluble. I'm going to look on my table here. My table is telling me that actually most sulfate-containing compounds are indeed soluble. But there are a few insoluble exceptions here, and one of those insoluble exceptions is when sulfate is paired with calcium, right? So this is one of those insoluble exceptions, so it is indeed insoluble. And what about magnesium sulfate? Who thinks it's soluble? Raise your hand. Insoluble, excellent. All right, so this is indeed soluble, because again, most sulfate compounds are soluble, right? It's listed in this water-soluble compounds. And there are a few insoluble exceptions, but magnesium is not among them, right? Magnesium is not listed here, so we can say that this is indeed a soluble compound. Okay, we can notice that our chart is broken into these 2 parts here. We've been focusing on this very top portion here. The bottom portion is very similar. You just got to be careful because your columns are kind of switched here. All right, so if we look here, for example, phosphate is one of these listed here. What this table is telling me is that most sulfates out there are insoluble compounds. All right, so any generic sulfate that you pick is most likely insoluble, except these few soluble exceptions here. Right, so there are a few exceptions to the rule where phosphate is paired with one of these few ions here, and that would make that compound soluble. right? But our columns are kind of switched here. Okay, so then let's do another one. All right, I'm going to put down 2 more, and you're going to tell me whether these compounds are soluble or insoluble. Okay, potassium carbonate and strontium carbonate.
Is the table going to be posted on campus?
Yeah, that's what I showed you at the beginning of class is where it was posted.
Oh, my bad.
Yeah. Under the introduction, that first page in the week 6 module.
Okay.
All right, so potassium carbonate, what do we think? Soluble or insoluble? So this one is indeed soluble. Most carbonate compounds, carbonate's listed right here on my table. My table's telling me that most carbonate compounds are actually insoluble, but one of the soluble exceptions listed here is when it's paired up with a potassium ion, right? So indeed that compound would be soluble. And then what about strontium carbonate? That one's insoluble, right? Because again, most carbonates are insoluble, and there are a few soluble exceptions here, but strontium is not listed as one of them. All right, so if it's not in that soluble exceptions column, it's going to be insoluble. Okay? Cool. So using this table here, again, we can look up and figure out whether an ionic compound is soluble or insoluble. By soluble, we mean it's going to dissolve in water. We can create this aqueous solution with it. If it's insoluble, it will not dissolve in water. All right? So looking up a particular compound, that's all well and good. Really what we're going to be using this for, the big thing, the hard thing we're going to be using this for, is to predict the products of a certain type of reaction. And these are what are called precipitation reactions. Okay, last class we talked about how acid-base reactions are this subcategory of double displacement reactions. These are yet another subcategory, right? So these are also just double displacement reactions. And we can remind ourselves what I mean by that if we have 2 compounds, A and B, our compound AB plus C and D. In this reaction, what we're going to see is A and C switch places. And we're going to be talking about ionic compounds. So what we're going to do is swap our cations. So now we're going to find that C is paired with B. I messed up my coloring. C was green, is paired with B, and A is paired with D. Right? So these are our double displacement reactions. These precipitation reactions are going to follow this same pattern here. All right? So a precipitation reaction is what happens when you mix 2 aqueous solutions and produce an insoluble solid product. right, you take these two beakers that have two different aqueous solutions in them. They're clear and colorless most of the time. Some of them have color. Mostly in chemistry, we're pretty boring color-wise, right? So you take these two clear colorless solutions and you mix them together, and all of a sudden this precipitate forms, this solid forms. You got a bunch of chunky stuff floating around in your solution. And that's because you've created one of these insoluble ionic compounds. All right, so these are one of the ones that we're going to have to predict the products for of these reactions. So let's take a look here. We're going to take barium chloride, a solution of barium chloride. And we're going to mix it with sodium sulfate. Okay, so we need to be able to predict the products of this reaction here based on the fact that it's a double displacement reaction. All right, so step one, we're going to swap our cations. All right, in my double displacement reaction, A is trading places with C. Right, they're swapping who they're paired with here. And so that's exactly what we're going to do. We're going to swap our barium and our sodium. Okay? So now we have our barium paired with our sulfate, but we got to be careful here about our formulas. We're going to do this the long way here. Barium chloride is a barium ion based on our periodic table. Let's just move over real quick and look at one. What is the charge on that barium ion? +2 in this second column right here, right? So based on where barium lives on the periodic table, I know it has a +2 charge. And chloride has a -1 charge. Sodium has a +1 charge based on where it lives on the periodic table. And what about sulfate's charge? -2. All right, look, so these were one of these 4 polyatomic ions that I told y'all you just have to know, right? Now, I'm not about cutting corners, but let's think about this logically here. We're going to have, as an addition to our constants page, this solubility table, right? And on this solubility table is listed each one of these polyatomic ions that we learned about here. All right, so now we got a little bit of a cheat sheet here for our polyatomic ions. Cool? All right, there's a catch, of course. The catch is that there are a few extra ones listed here that I can ask you about now as well, right? And you're going to have this for this page here, but let's just make note there are a few extra ones that are listed here that we hadn't seen before. The acetate ion, the chlorate ion, the chromate ion, our hydroxide, we talked about that last class actually. And then notably here, this ammonium ion. The reason that I want to single out this ammonium ion here is that what's different about this polyatomic ion than all the other ones that we've seen up until this point? It's got a positive charge, right? So this is our one polyatomic cation here. So just something to make note of, all right? So we got this cheat sheet now of polyatomic ions, but I'm going to add a few extra in there as well that we got to be able to use. What's up?
The cheat sheet's going to be on the test included?
Yeah, this is just like all of our constants information. This is going to be on the test. This isn't anything you got to memorize. You don't got to memorize this table, right? This is a tool you got to know how to use. Okay, cool. So now we got no excuse. We got to know sulfate is -2. Okay, and let me just keep my coloring consistent up here, red and orange. Okay, so now we're going to pair the barium with the sulfate. All right, these two got to get paired together. And we got to pair our sodium with our chloride. So everybody take a second and give me the formula of these two products here. All right, so when I pair my barium with my sulfate, remember when you do these formulas, it's all about the charges, right? So you're going to play your swappy swap game, and then you have to fully reduce that formula. So this would be BaSO4. And if I put my sodium with my chloride and I play my swap game, this would be NaCl. Okay? Now, one big mistake that people make is that they look on the right-hand side, on the left-hand side, and they say it's Na2 and Cl2 in these formulas. So I'm going to say Na2Cl2. That is not how we put together our formulas. I understand there's that little 2 there. We'll take care of that little 2 when we balance our chemical equation. But remember, when you're putting your compound formulas together, it's all about the charges. That's all you're going to pay attention to is the charges of those ions. Make sure they're paired up correctly. Okay? So not Na2Cl2. That doesn't make any sense. It's NaCl. Right? So we're going to predict our products by swapping our cations. Right? That allows us to predict the products. And that's just following the scheme that this is a double displacement reaction. All these precipitation reactions are double displacement reactions. But we said that these reactions are going to form this solid product. All right, so notice that the thing that's missing from this my product side here are these states of matter. And that's what we're going to need to use our solubility table for. All right, so step 2, we're going to look up each of our products on our solubility table. All right, so I'm going to take my 2 formulas here, barium sulfate, sodium chloride. We're going to look them up, and we're going to determine whether they are soluble or insoluble. Let's get rid of all these markings here. So we got NaCl and BaSO4. Okay, everybody take a second and look up these compounds here. Tell me whether they are soluble or insoluble. All right, NaCl is what? Soluble. And what about barium sulfate? Insoluble. If we look up sulfate here, we see that most sulfates are indeed soluble, but there are a few insoluble exceptions, and barium is one of them. So this compound here would be insoluble. All right, so then how does that translate to the states of matter in our balanced chemical equation here? Well, if you look it up and it's soluble, that means it's going to stay in solution or get that AQ designation. But if it's insoluble, that means it's going to precipitate out and form a solid. All right, so our solid that's formed here is this barium sulfate. Our sodium chloride remains in solution. All right, so if you mix these 2 things together, you'd see this chunky solid business form, and that would be that insoluble barium sulfate. The bariums find their sulfates. They don't want to stay in solution, and so they form a solid. They precipitate out. All right, the last step that we got to do here in order to use this chemical equation in any sort of a quantitative way would be to balance. And that's where you would take care of the fact that you have these little 2's out front of your sodium and your chloride that haven't been accounted for, right? Is in that balancing step. All right, so in order to balance, I'm going to put a 2 out front of the sodium chloride on the product side, and I have everything balanced here. All right, so again, first step, we got to predict our products, and we do that based on the fact that this is a double displacement reaction, right? So my barium is originally paired with my chloride, and my sodium is originally paired with my sulfate, and I'm going to swap the sodium and the barium. So now the barium is paired with the sulfate, and the sodium is paired with the chloride. Once we have our formulas for our products, we're going to look them up on our solubility table so we can figure out which one of our products is soluble and which one is insoluble. The insoluble one is our solid precipitate that has formed. All right, and then last step, so that we can actually use this chemical equation in some sort of a quantitative way, is we got to balance it. All right, so this is one of these reactions that we have to be able to predict the products for. Some reactions I was like, look, I'm just going to give it to you. You're just going to trust me that it happens. This is now one that we should be able to use that tool, that solubility table for, and predict the products of this reaction. All right, so let's do another one. We're going to take a solution of magnesium chloride. We're going to mix it with a solution of silver nitrate. All right, I'm going to give you all a few minutes here to see if you can't take this all the way to the end here. Predict our products. That's by far the hardest step. The table's not too bad. The swapping of the cations is where it gets tricky. And again, it's all about the charges. right, so magnesium has a charge of +2. I can tell just by looking at my periodic table. And chloride has a charge of -1. I can tell by looking at my periodic table. Silver has a charge of +1. In an ideal world, we knew that that was one of these transition metal exceptions that always has a +1 charge. Or we could have figured it out from the fact that nitrate has a -1 charge. All right? And now I'm going to have to swap my cations. So I'm going to pair the magnesium with the nitrate. And the silver with the chloride. All right? I'm swapping my pairs here. Oops. For my magnesium nitrate, when I do my swap here, it tells me I need 2 nitrates for every 1 magnesium. So what am I going to have to do in my formula? Put it in parentheses. And then my silver and my chloride are both 1 and 1, so that's just AgCl2. It's just AgCl, sorry. All right, cool. So now we need to go to step 2. We need to figure out what the state of matter is of each of these compounds. So we're going to go to our table and look them up. All right, again, we have magnesium nitrate, Mg(NO3)2, and silver chloride. All right, so everybody take a second, see if you can't finish your chemical equation by putting in those states of matter and then finally balancing that chemical equation. All right, my table tells me that nitrates are soluble and that there are no insoluble exceptions. So if it contains that nitrate ion, it is definitely a soluble compound. My table tells me that most chlorides are soluble, but one of the insoluble exceptions is when it's paired with a silver ion. And so silver chloride is insoluble. So that means that in my chemical equation, the magnesium nitrate gets the AQ and the silver chloride gets the S. Okay, and then lastly, if I'm balancing my chemical equation, my magnesiums match 1 and 1. I get to my chlorines though, I have 2 and 1, so I'm gonna have to put a 2 out front over here. When I get to my silvers, now my silvers are imbalanced, 1 and 2. So I'm gonna fix that by putting a 2 out front here. All right, for these nitrates, for these polyatomic ions, if you see them on both sides, you don't have to keep track of nitrogens and oxygens individually. You can just keep track of nitrates, and it just makes your life a little bit easier, right? I have a nitrate on one side, a nitrate on the other. Let's just make sure I have the same amount. And indeed, I have 2 on both sides. So here's my balanced chemical equation for this precipitation reaction. All right? So these precipitation reactions, we got a little bit more work to do here because we can actually predict the products of these reactions. They're double displacement reactions, so in order to predict our products, first we got to swap our cations to get our formulas for our products. Then to get our states of matter, we got to use that solubility table, and then we just balance them like we do normal chemical equations. Okay, and the last thing we're going to learn how to do here is create what's called a net ionic equation. Okay, once we get our balanced chemical equation, we can create what's called a net ionic equation. And let's go through the process of creating this, and then I'll show you why it's useful here. All right? So step one is we're going to break up all aqueous compounds into cation and anion. And there is a very key word here that we don't want to gloss over, and that is aqueous compounds. All right? So importantly, do not touch any non-aqueous compounds. All right, I'm not going to break up this silver chloride over here because it is not an aqueous compound. It is a solid, so I'm not going to touch that formula there. Only the aqueous compounds. The other thing we want to put here, because this is a common mistake, is do not break up polyatomic ions. The nitrate ion is your anion in this formula. It shouldn't be broken up into nitrogens and oxygens. It should stay the nitrate ion. All right, so let's go through this, and let me show you what I mean here. Magnesium chloride, I get to an aqueous compound. I'm going to break it up into cations and anions. So my magnesium chloride is going to become the magnesium ion. It's going to keep that AQ for being aqueous. And I'm also going to break this up into my chloride ions. But when I break this up, I get 2 chloride ions. Because in my formula here, there are 2 chlorides. All right, so magnesium chloride, AQ, is going to become magnesium ion plus 2 chloride ions. It's aqueous up top, so they're going to stay aqueous down here. I'm going to do the same thing to my silver nitrate. Since my chemical equation was balanced here, it says that I have 2 silver nitrates. So that means there are 2 silver ions and 2 nitrate ions. Okay, so importantly, let's just stop here and take note. My coefficient of 2 out front of my chloride came from the fact that there were 2 chlorides in this formula, right? So every 1 magnesium chloride has 2 chloride ions. My 2 out front of my silver and my nitrate came from my balanced chemical equation. The fact that in my balanced chemical equation, I have 2 silver nitrates. We want our net ionic equations to still be balanced, right? So those coefficients are going to carry. So now we're going to jump to the product side, and I want everybody to take a second and break up this compound here, the magnesium nitrate. Based on what we just discussed here, break up magnesium nitrate. All right, so magnesium nitrate, it's aqueous, so I'm going to break it apart. That would break up into 1 magnesium ion and 2 nitrate ions. And then what about silver chloride? I'm going to break that up. No, trick question, because it's not an aqueous compound. So all we're going to do is copy and paste it down here exactly as it appears in our chemical equation. All right, so if it's not aqueous, you just copy and paste. Let me make some room. Okay, this gives us what's called our ionic formula, but not our net ionic formula. So we got one more step here, which is to cancel exact matches from both sides. Right? Exact matches means formula, charge, state of matter. So can anybody see one of the things that I can cancel from this equation here, from my ionic equation? So the magnesiums appear on both sides. I'm going to cancel those out. Anything else I can cancel out? The nitrates appear on both sides. 2 NO3 minus 1 AQ. 2 NO3 minus 1 AQ. Those will also cancel out, right? So exact matches will cancel out from both sides. These are what we call spectator ions. So if now my net ionic equation is everything that's left over, my 2 chloride ions are combining with 2 silver ions to form 2 solid silver chlorides. All right, this is what we call a net ionic equation. And why we like net ionic equation, because it shows which ions are reacting. It's kind of like the meat of the chemical reaction here. Those things that we crossed out, the spectator ions, the magnesium and the nitrate, just like the name implies, they're just spectating. They're just watching this chemical reaction go down. They're not actually participating in the chemical reaction at all. In fact, we could have swapped out that magnesium for like a potassium or something like that, and the reaction would have gone on the exact same, right? So your spectator ions aren't actually involved in the chemical reaction. So your net ionic equation kind of simplifies things down to what's actually happening. In this reaction, what's actually happening is a silver ion is finding a chloride ion and coming together to form solid silver chloride. All right, so once we get our balanced chemical equation, we can go one step further and create this net ionic equation by breaking up all of our aqueous compounds into cations and anions, and then canceling things that appear on both sides. All right, one more thing real quick. In terms of formatting for your homework here, it's really important that you do your you do the sign and then the value for charges. All right, chloride you will see represented as Cl minus, Cl1 minus, and Cl minus 1. All 3 of these you would see in a textbook or on the internet, whatever it may be. Only the one where it's sign and then value is going to be accepted by your homework system. It's a math homework system. That's how mathematicians do charges. All right, cool. All right, so we'll finish this up next class.